Hi everybody, it's crazy, it's Monday, and it's time for the UPBGE video of the week. Now before I get started, gotta give a shout out to my trusted, because you guys rock, to my crazy fam, I love you guys. Now we're up to episode number 130, and we left off last week with BGE.constraints. Okay, and we also left off with the file basic underscore texture underscore replacement dot blend. As you notice, if you look up there, you'll see that there's got a 1. Save. Save a copy. Always save a copy. Trust me, it'll save you in the long run. There's many times where I didn't save and wound up having to redo everything. And try to do that from memory at my age is not good. Okay, so back up and save and back up again. Always have an alternate media to back up to. Always make a copy and always save. Those are the 3 basic things you can always do that will at least save you in the long run. Okay, so last week we left off with BGE.constraints, and we're going to go ahead and get started with that. If you played with this file that's up here, you'll notice that, you could do a lot of things with it, right? But hopefully you saved it as a 1 or something else, playing or whatever. Just hopefully you didn't change the one in your book. If not, you got to go back to the place where you get the files, which is all in the description below, which is the book and the files. You'll have to recopy that specific file back over to make it back new and see what happens. It's not good. All right, so let's go ahead and get started. The Bullet physics engine allows for advanced control over the physics simulation in your game. Using Bullet as a back end, this module, formerly known as physics constraints, allows you to create and set up rigid joints, dynamic constraints, and even a vehicle wrapper. The constraints functionalities make sense only when you understand the context in which they are to be used. With physics dynamic objects, dynamic objects. Therefore, this module is covered in the previous chapter on game physics. So go back to the last chapter, which is chapter 6, and you'll find all that information right there. Okay, math utils, math types and utilities. Math utils is a generic module common to both Blender and the game engine. There are a lot of methods to facilitate your script in handling 3D math operations. You won't have to reinvent the wheel every time you need to multiply vectors or transpose matrices. Simply use the mathutils classes and built-in methods frees you to invest your time in something far more important, relearning all of the long forgotten math lessons you skipped. Yeah, that was definitely me. All right, so unless your background is in math, physics, or engineering, you won't use this module anytime soon. For those already familiar with the passionate secrets of math, you'll be glad to know that those modules' functions are mainly self-explanatory. Names such as cross, dot, slurp, what? And a quick look at their specifications will be all you need to know to start working with them. Nevertheless, newcomers often use this module without even knowing it. Every time you change an object position, get the vector from an object, or apply a rotation, you are using mathutils classes and methods. Therefore, it's good to have this module as a reference for further studies and more advanced coding. We all get there eventually. We do. Yeah, eventually you'll play with a little bit of programming, and oh man, I got to have this mouse look feature, or I've got to have this feature, I've got to have that feature. How do you get the car suspension to work? That type of deal. You'll wind up looking for codes that can actually help you, that you can plug into your into the components and make them work. Okay? We are going to present the 4 available classes in this module: vector, matrix, Euler, and quaternarian. For a list of the available methods, refer to the API documentation. Vector. This class was already presented in the KILLxxGameObject class, and in the script example, it behaves like a list object with some advanced features. For example, swizzle and slicing, expanded with its instance methods. Some of those methods are reflect, dot, cross, and normalize. A reoccurring problem that new Python programmers have is with list copying. If you forgot to manually copy the list when assigning it to a new variable, you end up with two variables sharing the same list values forever. Each of the variables becomes a pointer to the same data. Okay? The same behavior happens with vectors. Look at the difference. New underscore vector equals old underscore vector. If you change new underscore vector to, or let me reread that. If you change new underscore vector, you will automatically change old underscore vector, and vice versa. New underscore vector equals old underscore vector, brackets, colon, brackets. The new underscore vector is a new independent list object initialized with the old vector values. New vector equals vector dot copy parentheses. Is that parentheses? The little half brackets, half moon brackets, or quarter moon brackets. New vector is a new vector and independent copy of old vector object. Okay, so basically what they're saying is that new vector equals old vector, okay, is the same thing. It's like both hands, okay, facing the same way. Whatever you do with this hand's going to do. It's a mirror copy. Okay? If it's new vector equals old vector with the little square brackets with the colons in the middle, then that is going to make the new vector list independent from the old vector list, but have the old vector list values. Okay? New vector equals vector dot copy with the quarter moon brackets is the new vector, okay, with a copy of the new vector over here. So if you change this one, nothing happens in this one. This one stays the same. Okay? Matrix. I'm going to take a drink. While vectors behave similarly to list matrices, matrices have, or strike that. While vectors behave similarly to lists, matrices behave similarly to multidimensional lists. A multidimensional list is a list of a list, organized either in columns or rows. So a list and a list, or a list and a list. The same thing as what you would see in Excel. You would see a list of stuff and a column of stuff and a row of stuff. Well, a row of them would be multidimensional. Okay, so you can do either one. It's like looking at a spreadsheet. While in Python, a list of a list is always the same. Matrix underscore row equals square bracket 1, 2, 3, square bracket, comma, square bracket 4, 5, 6, square bracket, comma, and so on. Okay, in a mathutils.matrix, the data can be stored differently according to the matrix orientation, row or column. Following, you can see how the order of the elements in the matrix changes according to its orientation. Note, this is not actual Python code. Okay, so I'm going to switch over there so you can see it. Okay, which is it's not actual Python code, but this is column, or see, this is row, this is column. Okay, so this does it in a row, and it's actually going to put all these over here. Okay, and then the column is going to put these this way. Okay, so it's using slide bars and then these down below. Okay, it's important to be aware. Let me put you back over here so you're not being blinded by white light. It's important to be aware of the ordering of your matrices. Otherwise, you end up using a transpose matrix for your calculations. Since all the game engine internal matrices, orientation, camera to world, and so on, are column major oriented, you will be safer sticking to the standard. So you'll be sticking more to the column major standard, is what they're saying. Okay? If your matrices represents a transformation matrix, rotation, translation, and scale, you can get its values separately. Matrix 2 dot 2 underscore quaternion, and then quarter moon brackets, and matrix dot 2 underscore Euler will give you the rotation part of the matrix in the form you prefer. See next section. So that's the next section we're going to be working with. And matrix dot 2 underscore translation brackets and matrix dot 2 underscore scale brackets will give you the transformation and the scale vector respectively. Okay? So if you're using the quaternion and the Euler, it'll give you the rotation part of the matrix. Okay? And then if you're using the translation and the scale, it will give you the translation and the scale vector respectively. Okay? See, where are we at? Yeah, we're right at around 11 minutes. I'm going to go ahead and stop with, break it off right here at E. Euler and quaternion. Yeah, because we got a little bit more to go, and next after that is the alter. Well, I could just go ahead and finish it. Let's just go ahead and finish this one off. I'm going to go ahead and do that. I think it would be a little bit easier because the next one is audio, and I love audio, so that one I want to save for next week. All right, so E. Euler and quaternion. You know how to say that? Say it to me and send it to me because I don't know how to say that one. All right, so E. Euler and quaternion are different rotation systems. The same rotation can be represented using E. Euler, quaternion, or an orientation matrix. Okay, so Gorilla CG. You can find 2 great video tutorials on the Gorilla CG Vimeo channel that explain and compare the 2 rotation systems. The Euler rotations explained is, I'll kick it over and you just write this in there. It will give you the Euler rotations, and the next one will give you the rotation problem, which is this one right here. Okay, so write that down and put it in your browser. Take a look. I'm not gonna go ahead and put it in the description because I've already got a lot of stuff in the description as it is. But if you're following along in the book, all you have to do is actually click on those. Okay. When you convert an orientation matrix to Euler, matrix dot to Euler, you get a list with 3 angles. They represent the rotation in the X, Y, and Z axis of the object. In the navigation system script example, we are using this exact method to determine the horizontal camera angle. You can find this usage in the function fly underscore to underscore walk brackets. Lines 190 to 199 of navigation underscore system dot py, or in the early pages of this chapter. Conversion between different rotation forms. You can convert an orientation matrix to Euler, and a Euler to a quaternion, and a quaternion to an orientation matrix, and on and on and on. Okay, so original underscore matrix equals Matthew Tills dot matrix dot rotation math dot pi comma 3 comma x in quotes and then brackets. Okay, converted underscore matrix equals original matrix to E. Euler quotes or brackets dot 2 underscore quaternion brackets 2 dot underscore matrix, quotes, and not quotes, brackets, sorry, to E dot to E Euler, and so on and so on and so on. Okay. In this example, converted underscore matrix ends up as the same metric as the original matrix. Okay, so I'm going to go ahead and end it there. That's going to be at the bottom of page 67. And let me kick over to here. Nope, wrong one. Oop. If I can get them right here. What happened to my background here? There we go. All right. I've been dancing everywhere today. Okay, so we're going to leave off. I hate when it does that. We're going to leave off on page 67, at the bottom of page 67. And we're going to start with the odd, or the audio system, for next week. And audio systems are fun. I like playing with those because I'm an audio fan. So we'll leave it that for next week. Audio systems on page 67 at the bottom. We'll see y'all next week.